Okay, thank you. As you know, of course, most of the universe is made of hydrogen-helium mixtures, and so there's a fundamental reason for trying to understand whether there might be pressure-temperature conditions under which hydrogen and helium become immiscible. But in terms of, there's also a very specific reason for looking at this problem, and that has to do with the luminosity of giant planets. Next slide. Can I control the slides?
Yeah, just keep.
Okay, great. Okay, before getting to Saturn and explaining the title of this slide, let's start with Jupiter. Jupiter, of course, is one of the brightest objects in the night sky, and the question is, why is it as bright as it is? If you just look at equilibrium with solar radiation, it would have a much lower effective temperature of only about 110 Kelvin. So Jupiter is glowing more brightly than that. It's releasing energy from its inside, and ultimately the source of this energy is the accretion of the planet. If you assume that the composition stays constant with time throughout the depth of the planet and that the entropy is uniform in the interior, it's fairly straightforward to do a calculation of the thermal evolution of the planet. And if you do that for Jupiter, you end up with thermal histories that agree very well with the observed effective temperature of about 125 Kelvin today. If you play the same game for Saturn, you end up with kind of a disaster because Saturn very rapidly cools to temperatures below the observed effective temperature today. And so people have wondered, why does Saturn glow more brightly than these thermal history calculations would suggest? And one possibility is that there's an extra energy source within Saturn that's doing this. In the 1970s, Salpeter and Stevenson suggested helium rainout as this extra energy source. The basic idea is that in the shallow part of the planet, hydrogen and helium are miscible in each other. Then, as you go to higher pressures, helium becomes immiscible, it starts raining out, and you end up with a planet that's helium enriched down here and helium depleted up here. And this may, in fact, explain some of the observed helium depletions that we see in the shallow parts of these giant planets. The gravitational energy release then provides the extra energy source. If we start to think about the microphysics of what is going on here, hydrogen and helium are very soluble in each other at low pressure because the H2 molecule and the helium atom have a very similar size, and mixing objects of similar size is very easy to do. However, as Miguel Morales pointed out in the last talk, as you go up in pressure, hydrogen undergoes a structural transition from dominantly molecular to dominantly atomic at higher pressure, and the hydrogen atom is much smaller than the helium atom, and helium becomes immiscible, and you get this rainout. Okay? So this is sort of a summary of the conditions under which helium droplets may form. Here's the molecular to atomic transition according to our calculations, and helium is quite miscible at low pressure, but then as you cross this molecular to atomic transition, very rapidly the stability field for helium droplet formation expands very rapidly before flattening out at higher pressures. And this is from Morales' calculation here. This is from Lorentz using a very similar type of calculation. And if we compare now to the estimated pressure temperature conditions inside the giant planets, what we see is that according to Morales' calculation, helium rainout should not occur in Jupiter at all, whereas it should occur in Saturn over a limited range of pressure. These are some older calculations based on perturbations to the free electron gas from DeWitt and also from crystalline structures from Pfaffenzeller et al. Well, we were motivated to reconsider this problem for two reasons. One is some of the things that Morales showed you in the last talk is that the properties of these systems can be very dependent, much more so than many of the other systems we're used to, very dependent on the details of the exchange correlation functional or the level of theory. And so we wanted to investigate that. We also found from our calculations evidence that system size matters more than people had suspected before, and much larger systems may be necessary to accurately capture the physics of these systems. So what we did is first principles molecular dynamics. Some of the computational details are given here. Another innovation over previous calculations is that we use a constant pressure ensemble, which is in principle more robust because the chemistry of helium separation is in principle a constant pressure process, so it gives us a much better handle on that. And of course, the physics that's driving the dynamics in these simulations is from the electrons. How do you calculate those forces? What we've done is to use density functional theory. Solving the Schrodinger equation completely is very difficult. There are quantum Monte Carlo methods, but they're very difficult to apply to fluids. And so the advantage of density functional theory is it's based on these Kahn-Sham equations, which are also formally exact, but unlike the Schrödinger equation, give you a good starting point for approximations. One of the reasons for that is that the central quantity is the charge density, just the number of electrons per unit volume, rather than the full many-body wave function. And as it turns out, the many-body interactions between the electrons can be thought of in terms of an exchange correlation hole, an area of reduced charge density that each electron digs out for itself. And in many materials, you can demonstrate that this exchange correlation hole is very well localized, which accounts, in a way, for the success of some of the simpler approximations that Miguel referred to in the last talk, LDA or PBE, etc. We know there are other forces, and maybe it makes sense to include them. This is one that we all learn in introductory chemistry, the London force or dispersion force or van der Waals force, where fluctuation in the charge density in one atom induces a dipole in a neighboring atom and an attractive dipole-dipole interaction. Including these non-local effects is known to be important in many systems. This is just one example of many from graphite. If you use the traditional approximations, graphite isn't bound at all, it just falls apart. But if you include these non-local interactions, then you get a very good agreement with experimental energetics. We use the VDW-DF2 form of this non-local correlation, which Morales had also used before. And indeed, we find good agreement with him, finding that including these non-local forces produces a very different molecular to atomic transition at much, much higher pressure. So here's the PBE molecular to atomic transition here, and here's the VDW molecular to atomic transition here at more than twice the pressure. If we look at a blow-up of the transition region here, what we found is that the nature of this transition also depends on system size. That perhaps surprisingly to us, we needed very large systems to converge the properties of this transition. So our sort of central result, 1,024 atoms, is in the large purple circles. But if you go to 512 atoms, you get quite a different transition pressure. We are converged, though. As you go to 2,000, we get the same result. We do find a van der Waals loop, a complete van der Waals loop, which you expect in these NVT conditions, and so we can characterize quite accurately the transition pressure and the change in volume across the transition. So VDW matters, at least at low temperatures. What about at high temperatures? So what I've done also is to compare here. I'll be focusing on conditions of 10 megabars and 10,000 Kelvin, and at those conditions, pure hydrogen looks the same to PBE and VDW. Okay, so why should we care about this difference when looking at hydrogen-helium solutions? Well, one reason is that if you look at the structure of hydrogen-helium solutions, what you find is that if you start from pure hydrogen, you get a very simple liquid structure here, just an excluded volume effect, otherwise pretty much ideal gas-like. But as you add helium to the solution, what you find is that hydrogen molecules form, actually, even at these very, very high pressures and temperatures, far beyond the low temperature molecular to atomic transition. So at very helium-rich compositions, you get this well-defined molecular hydrogen peak. And so that gives us some reason for thinking that, well, maybe the exchange correlation functional matters even at these very high pressure temperature conditions. It also tells you that there's non-ideal mixing in this system. Okay, so here's our central result. What we have so far is the energy of mixing as a function of helium number fraction at two temperatures, 5,000 Kelvin and 10,000 Kelvin, both at 10 megabars. And what we find is a positive enthalpy of mixing here at both of those temperatures, and that's for 1,000 atoms. And what we found that these results were a bit different from previously published results. And to understand the difference, what we did is to run other simulations at a reduced number of atoms, just 256. And we do find a significant difference between these two results. So larger system sizes do matter at these conditions as well. In order to compare directly to Morales' earlier results, what we did is to take his non-ideal entropy of mixing directly added to our enthalpy of mixing, and we find Gibbs free energy of mixing curves in the blue here at 5,000 Kelvin and at 10,000 Kelvin. So the central result is that at 10,000 Kelvin we find that helium is miscible in hydrogen, whereas at 5,000 Kelvin it's immiscible, but just barely so. And the Gibbs free energies of mixing are quite a bit lower than what Morales had found at both of these conditions. Most of that difference we attribute actually to the difference in system size, rather than to the difference in exchange correlation functional. There may be some residual effects of exchange correlation functional here as well. So just to summarize some of that stuff, energy mixing does depend significantly on system size up to these very large numbers of atoms. It's more favorable in larger systems. The system size accounts for most of the difference with previous results, and the exchange correlation functional might also be significant as well, but to a lesser extent than the system size, we think. So just to summarize our results in the context of previous work, these are the previous results using PBE from Morales and from Lawrenson. This is our result using BDWDF2 and larger systems. And this is a bit schematic, but there's no doubt that our immiscibility temperature will be significantly lower than previous results. And this makes helium miscible in hydrogen at the conditions of Jupiter and Saturn, and so helium rainout, according to our results, is unlikely to occur in these giant planets. And so in conclusion, we do find this miscibility. Helium rain is unlikely. It might be important in extrasolar planets that are older or colder, and that other explanations should be explored for the excess luminosity of Saturn. Thank you.
We have time for questions.
Yeah. We have to be careful about demixing. We have found that demixing does occur for very, very long runs, and so we focus on the part that's still homogeneous to get the energetics of mixing. And can we go back? So the enthalpy of mixing is still positive. At 10,000 Kelvin, we don't get that problem at all. At 5,000 Kelvin, for very, very long runs, we do start to get demixing. But the fact that the enthalpy is positive, and also by looking at the structures in detail, we think we've overcome that. Something like 20 picoseconds. Yeah. Of course.
So it's very interesting, but in a sense, without really looking in detail, we can see around 20%, and it's very hard to tell what's going on. And in our case, we have to do 20 calculations with 0 and 20 just to be able to have some idea of what's really happening, because it's very easy to miss exactly when the critical point is, unless you do calculations very carefully. So just as that.
Sure. No, I agree with you, of course, and we're working on it. We're doing that. I think the conclusion, just based on the energetics, though, is quite clear that the larger systems are more favorable to miscibility.